There is a courtyard in New Delhi that most tourists walk through without pausing long enough to understand what they are actually looking at. It sits at the center of the Qutb Minar complex, surrounded by carved stone arcades and the quiet ruins of what was once the oldest mosque on the Indian subcontinent. The visitors who arrive in the early morning, before the heat has fully settled into the stone, almost always stop at something unexpected, not at the famous minaret behind them, not at the ancient inscriptions overhead, but at something smaller and far stranger that stands at the open center of the courtyard, without ceremony, without enclosure, and without any explanation that comes close to adequately describing what it is. It is an iron pillar, 7.2 meters tall, forged from wrought iron so pure that modern metallurgists find it difficult to categorize using conventional descriptions. It weighs somewhere above 6,000 kilograms, and it was erected sometime between 300 and 400 of the Common Era, 16 centuries ago, by craftsmen of the Gupta Empire working with fire, clay, charcoal, and a body of knowledge whose exact nature remained a formal mystery to modern science until the early years of the 21st century. Since the day it was planted in that courtyard, the pillar has stood in the open air of northern India. It has endured 1,600 monsoon seasons. It has been exposed to the corrosive humidity that clings to the Gangetic Plain for months at a stretch, to the atmospheric oxygen that has been dissolving iron objects since before human beings first learned to smelt ore from stone. It has received no protective coating, no chemical treatment, no enclosure of any kind. It has not rusted, not in any meaningful sense. There is a surface darkening the kind of deep patina that exposure over long periods naturally produces. But the iron beneath that darkened surface is structurally intact, dimensionally stable, and in a metallurgical condition that modern corrosion engineers describe with a clinical precision that barely conceals their discomfort. An iron object of this age, left outside in this climate, should not exist in this condition. The chemistry, as it is conventionally understood, does not allow it. For most of the 20th century, various explanations were proposed, examined, and quietly set aside. Then, in 2002, a research team published an analysis in the journal Current Science that finally identified the mechanism. The pillar's surface had generated, through its own internal chemistry, a thin protective layer of a compound called mica-white, a crystalline structure of iron, oxygen, and hydrogen that had self-assembled at the metal's surface over time and sealed the iron beneath it from further oxidative attack. This layer had formed because the wrought iron used to build the pillar contained an unusually high concentration of phosphorus, a compositional characteristic, whether deliberately chosen or inherited from a specific ore deposit that initiated this protective chemistry. Once the layer formed, it held. It has been holding for 1,600 years. The formal relationship between phosphorus content in wrought iron and the self-generation of this kind of protective surface chemistry was not documented by Western corrosion science until the 1980s and 1990s. The people who built this pillar were producing the result in the 4th century of the Common Era. That distance between the creation of an effect and the eventual scientific explanation of it is where the real weight of this object lives. Not a question about lucky accident or ancient guesswork, but something far more unsettling. A question about the nature of knowledge itself. About what was known, by whom, carried through how many generations, transmitted through what means, and why so much of it managed to disappear from the record as completely as it did. The pillar does not explain itself. It simply stands in the Delhi courtyard, patient and dark, refusing to corrode, and it waits for the question to be asked at the correct scale. But Delhi was not alone. Across 3 continents and more than 4,000 years of human history, it was not an isolated puzzle waiting quietly in a courtyard. It was one thread in a pattern so large and so consistent that recognizing it changes something fundamental about how the story of human capability should be told. Consider what the conventional history of metallurgy tells us about sub-Saharan Africa around 1,500 years before the Common Era. According to the standard framework, the region was firmly in what historians call the Stone Age, its peoples living without metalworking of any kind, untouched by the copper and bronze technologies spreading through the ancient Near East. That is what the textbooks say. But in the highlands of what is now northwestern Tanzania, carbon steel was being produced in furnaces that operated at temperatures modern engineers initially classified as unachievable with the bellows technology of the period. Not iron, steel. The harder, stronger, more chemically complex material that Western industrial civilization would not manufacture consistently until the 19th century. Consider the Andean highlands of South America, where civilizations were alloying platinum, a metal with a melting point so extreme that conventional pre-industrial furnaces cannot approach it into gold objects using a sintering technique that modern jewelers independently rediscovered in the 20th century. The Andean smiths were working with this process approximately 2,000 years before the rediscovery happened. Consider China during the early Zhou dynasty, 7 centuries before the Common Era, where cast iron, the foundational material of the European Industrial Revolution, the substance from which James Watt's steam engines and the world's first iron bridge were made, was already in routine production for agricultural tools and weapons. The gap between China's first cast iron and Europe's first cast iron is approximately 1,200 years. Each of these achievements sits at a different point on the map. Each belongs to a different culture, a different tradition, a different corner of the human story. And yet, each one shares the same quality as the pillar standing in Delhi. It represents a level of metallurgical knowledge that the conventional framework says should not have existed when the evidence shows it clearly did. Looked at one at a time, they are interesting anomalies, curiosities to be noted and set aside, but they are not one at a time. They are many, scattered across every inhabited continent, distributed across millennia, consistent in their message, and impossible to dismiss as coincidence once you have seen enough of them. The question is not how these people managed to be so far ahead of their time. That framing is already wrong. The question, the one that reshapes everything once it is properly asked, is why we ever believed they were behind it. There is a structure in mathematics called a lattice. It is a geometric form made of intersecting lines that, from any single angle of view, appears to be a series of disconnected points or crossing lines without obvious organization. But viewed from above, from the correct elevation, at the correct scale, the same structure resolves into a coherent, interconnected whole. Every point connects to others. Every line is part of a larger geometry. What looked like fragments becomes a unified architecture. The metallurgical achievements of the ancient world work in precisely this way. Examined individually, culture by culture, excavation by excavation, each one appears to be a local anomaly, an interesting exception to the rule, a data point that doesn't quite fit, best noted in a footnote and absorbed into the larger narrative without disturbing the narrative's fundamental shape. But when they are laid against each other, across all the continents and all the centuries at once, something else emerges. A pattern, a shape, something that looks less like a collection of accidents and more like evidence of a connected, persistent, deeply sophisticated human relationship with metal, one that runs far deeper in time and far wider across geography than the version of history most of us were handed. This is what the iron lattice is. Not a single mystery with a single answer, not a conspiracy with a hidden architect. It is the shape that human knowledge makes when you stop filtering it through a framework that was built to exclude most of human history from serious consideration. It is what you see when the map is finally allowed to show the whole territory. The story ahead moves across 10 chapters, each one adding a section of that territory to the map. It will travel to Africa, to India, to China, to the islands of Southeast Asia, to the high Andean plateau of South America. It will examine the machines these people built, the knowledge they carried, the methods they used to transmit that knowledge through generations that had no writing. It will look at what has been lost, and how it was lost, and whether any of it can be recovered. And it will arrive, at the end, at a conclusion that is simpler and more consequential than any single piece of evidence that leads to it. The Iron Age did not begin when historians said it did. It began much earlier, and in places the textbooks never thought to look. In 1836, a Danish museum curator named Christian Jørgensen Thomsen faced a practical problem. He was reorganizing the prehistoric collection at the National Museum of Denmark in Copenhagen, and he needed a system, some organizing principle, that would allow visitors to move through the collection in a logical order, and understand the relationship between the objects on display. His solution was straightforward and, in its original context, entirely sensible. He arranged the artifacts by material. Objects made of stone came first. Objects made of bronze came next. Objects made of iron came last. Stone Age, then Bronze Age, then Iron Age, a sequence based not on any theoretical framework about human progress, but on the physical stuff that human hands had left behind in the Danish earth. Thomson had no intention of describing the history of all human civilization. He was organizing a storage room. He was making a practical decision about how to sequence a museum collection in a way that would be legible to the general public. And for the collection, he was working with objects drawn primarily from Scandinavian and Northern European archaeological sites, assembled within the specific cultural context of 19th century European scholarship. The sequence he chose was a reasonable one. What happened next was not his fault, and it was not deliberate, and it is not any single person's responsibility. What happened was that a curatorial convenience became a universal law. Over the following decades, Thomson's three-part sequence was adopted by archaeologists, historians, and educators across Europe and eventually across the world as a framework for describing not just Northern European prehistory, but the entire developmental trajectory of human civilization. The Stone Age, the Bronze Age, the Iron Age. This became the grammar of human progress, taught in every school on the planet, built into every textbook, assumed by every student who ever sat through a history lesson about the ancient world. The problem is that the framework was built entirely from European evidence and European assumptions. The idea that technological advancement moved outward from one region in one sequence, that the Near East and Europe were the originators, and that the rest of the world followed at a measurable lag, was never a conclusion drawn from global evidence. It was a projection of regional data onto a map that was much larger than the data could actually cover. The civilizations of sub-Saharan Africa, South Asia, East Asia, and the Americas were not studied in building the framework. They were expected to fit within it after the fact. And when their evidence refused to fit, when their iron appeared earlier than the framework allowed, when their steel turned up in places the sequence said should still have been using stone, the instinctive response was to question the evidence, not the framework. This is how the timeline became a filter, quietly and without any explicit decision. When archaeologists began finding iron objects in stratigraphic contexts that predated the official Iron Age by centuries, the question that arose first was not, does this mean the timeline is wrong? The question was, how was this object placed here? Was the context contaminated? Was the dating method reliable? Was the object moved from a later layer to an earlier one by human activity or by natural forces? The framework survived these encounters intact because survival was the default. The evidence was adjusted. The system held. There is a specific name for the mechanism that does this adjusting. Archaeologists call it contextual contamination, and it is a legitimate interpretive tool for genuine cases where artifacts have been displaced from their original deposits by later human disturbance or by geological processes. Objects do move. Sites do get disturbed. Careful archaeological judgment requires the ability to identify when an artifact's apparent context is not its actual context. But like any legitimate tool, this one can be misapplied, and in the history of metallurgical archaeology, it has been misapplied with a consistency that is difficult to attribute entirely to careful scholarly judgment. In 1837, workers at the Great Pyramid of Giza found a piece of iron embedded in the masonry during repair work. The artifact was brought to England and eventually analysed. Its context, if genuine, would place it at the time of the pyramid's construction, approximately 2600 BCE, several centuries before Egypt's officially recognised Iron Age. The initial response was methodologically appropriate. The context was questioned. The possibility of contamination was raised. Further study was called for. But the further study produced a result that complicated matters rather than resolving them. Subsequent analysis found that the piece contained traces of gold, suggesting it had been treated or alloyed in ways inconsistent with simple meteoritic iron, which would have been the easy explanation. More complex hypotheses were required. Those hypotheses were never fully pursued. The object was reclassified, placed in storage, and the conversation effectively ended. A similar pattern emerged with the meteoric iron objects found in pre-dynastic Egyptian burials, beads, and small implements made from iron long before Egypt had any formal smelting capability. The initial explanation was that meteoritic iron required no smelting knowledge and could be cold-hammered into shape by anyone. This was true, but incomplete. The beads showed evidence of heating and reshaping that went beyond simple cold working, suggesting a level of understanding about iron's thermal behavior that the Stone Age timeline did not accommodate. This complication was noted in papers. It was not resolved. The timeline continued. What makes this pattern significant is not any single case, but the consistency of the direction. The anomalies do not fall randomly across all cultures and all time periods. They cluster in specific geographies: Africa, South Asia, East Asia, the Americas, and they consistently point in the same temporal direction toward dates earlier than the framework allows. This is not the signature of random measurement error or occasional contamination. This is the signature of a systematic bias operating on a global scale through a framework that was never designed to account for the civilizations it was being applied to. The framework was measuring the wrong things, in the wrong places, using the wrong assumptions and calling the result universal truth. Strip every textbook away. Set aside the framework entirely. Ask only what the physical evidence, the objects, the ore deposits, the furnace ruins, the carbon dates actually shows, on its own terms, without a preconceived sequence to slot it into. What emerges is a different map entirely. In the Great Lakes region of North America, indigenous peoples were hammering native copper that occurs in its metallic form at the surface, requiring no smelting into tools and ornaments as far back as 8,000 years before the Common Era. This is not smelting in the technical sense, but it is deliberate, systematic metalworking. The selection of specific copper pieces, the knowledge that repeated heating, followed by cold hammering, changes the metal's hardness, the transmission of that knowledge across enough generations to produce a sustained and geographically widespread tradition. It predates the Old World Copper Age by millennia. The textbooks rarely mention it. In what is now Serbia, in the Vinča culture, copper smelting, genuine smelting, reducing ore to metal through deliberate high-temperature chemistry, was occurring around 5,500 years before the Common Era. This is 3,000 years before the conventional beginning of metalworking in the standard chronology, which places the Copper Age in the Near East around the 4th millennium BCE. The Vinča sites show not just evidence of smelting, but evidence of systematic practice, specific ore selection, controlled firing temperatures, repeated technique applied to multiple objects. This was not an accident. It was a craft. In sub-Saharan Africa, high-carbon steel, not iron, but steel, the more complex and technically demanding material, appears in the archaeological record before 1000 BCE in multiple locations. These regions appear in the conventional timeline as Stone Age societies at the same date. The physical evidence says otherwise. The gap between what these objects show and what the official chronology claims is not distributed randomly. It does not underestimate European civilizations. It does not underestimate Near Eastern civilizations. It systematically, consistently underestimates civilizations in Africa, in Asia, and in the Americas. That pattern is not neutral. It is the shape that a European-centered framework makes when it is applied to evidence it was never built to read. And understanding that shape, understanding where it comes from and what it costs, is the first and necessary step towards seeing the history that it has been obscuring. The corrected timeline, read without the framework filtering it, also reveals something that the conventional story entirely misses. The sheer antiquity of the human relationship with metal is not merely interesting as a footnote about dates. It changes what is possible to claim about the nature of that relationship. A tradition of copper working that has been operating for 8,000 years, as the Great Lakes evidence implies, is not a recently acquired skill. It is a multi-generational institution. It has had time to develop complexity, refinement, and specialization that a younger tradition simply cannot possess. It has had time to develop the kind of accumulated wisdom that only deep time produces. The specific knowledge of which ore sources yield better material, which processing sequences produce better outcomes, which seasons and weather conditions affect the smelting process, and how to compensate for them. A tradition that old is not primitive in any meaningful sense of the word. It is ancient, which is something entirely different, something that implies depth and sophistication precisely because of how long it has had to develop. The question now is not when the Iron Age truly began. The question is what the people who worked metal long before the textbooks acknowledged them were actually doing, and what they actually knew, and where their knowledge came from. That question pulls the story forward, into the oldest fire, toward the first smiths who ever looked at a stone and understood that hidden inside it was something that could be made to flow. No one decided one morning that they would smelt copper. The idea did not arrive complete, theoretical, ready to be applied. It came slowly, through observation that accumulated over generations, in ways that were not recognized as accumulation while they were happening. A stone placed near a fire behaves differently from a stone placed away from it. Certain stones, in certain fires, under certain conditions of heat sustained long enough, begin to change, not to crack or to blacken in the ordinary way, but to weep. A thin, bright liquid gathers at the stone's hot face and runs toward cooler ground, and when it cools, it is no longer stone. It is something harder and stranger and more useful than stone. It can be beaten. It can be shaped. It holds an edge. The cognitive leap required to turn this observation into a repeatable process is immense, and we tend to underestimate it because we live on the far side of it. The understanding that a solid and a liquid can be the same substance in different states, that heat is not just destruction but transformation, was not obvious. Nothing in daily human experience, before this, had prepared anyone for it. Wood burns and becomes ash. Stone cracks and becomes rubble. Water flows and becomes steam and then returns. But metal flows and then becomes, in its cooled form, something categorically new, more useful than what it was, more useful than almost anything the natural world offered directly. This was not just chemistry, it was a new relationship between human intention and the physical world. The Vinča culture of the Central Balkans, the people who inhabited the river valleys of what is now Serbia, Romania, and Bulgaria, were operating one of the oldest confirmed copper mines and smelting traditions in the world by around 5,500 years before the Common Era. When archaeologists excavated their sites in the 20th century, they did not find evidence of casual, occasional metalworking. They found evidence of systematic practice, specific ore types selected and transported from particular sources, fired clay crucibles shaped in consistent forms, waste slag with chemical signatures indicating controlled temperature processes, and finished copper objects whose alloy compositions reflected deliberate, repeatable decisions about the material's preparation. This was not a lucky accident passed down as a ritual. This was knowledge accumulated, organized, transmitted, and refined across generations in a society that left no written records of any kind. The Vinča had no periodic table. They had no concept of atomic structure, no vocabulary for describing the chemical processes they were managing. What they had was something older and in some ways more demanding than theoretical understanding. They had procedural mastery. They knew, through direct experience accumulated across lifetimes, exactly what to do, in what order, with what materials, under what conditions. They knew this the way a skilled carpenter knows which grain to cut with and which to cut against, not from a textbook, but from the hands, from the eyes, from the material itself, teaching them its rules through resistance and yield. The excavations at Pločnik, one of the largest Vinča settlements, produced something that stopped archaeologists mid-interpretation. A copper axe, dated to approximately 5,500 BCE, whose composition and construction reflected a multi-step production process. The ore had been smelted, the copper cast into a rough form, then cold-worked and annealed in specific alternating cycles to produce a tool whose hardness profile harder at the cutting edge, tougher at the socket, was the result of deliberate thermal and mechanical processing, rather than accident. This is not the product of a civilization that had recently discovered that hot stones could yield liquid metal. This is the product of a tradition that had been working with copper long enough to understand its response to different processing histories, to have developed and transmitted the specific sequence of operations that produced the desired result, and to have standardized that sequence to the point where its outcomes were predictable. The Vinča copper tradition represents what archaeologists now call the Chalcolithic period, the Copper Age in the Balkans, and it predates the equivalent stage of metalworking in the Near East, which the conventional framework designated as the primary origin of Old World metallurgy by approximately 3,000 years. This chronological precedence has been confirmed and reconfirmed by multiple independent dating techniques across dozens of sites. It is not disputed. What remains under-discussed is what the precedence implies, that the story of how metalworking knowledge spread across the ancient world needs a different origin point than the one usually cited, and possibly a different directionality of transmission than the one usually assumed. And here is where the observation that changes everything enters. The Vinci did not invent this knowledge from nothing. The sophistication of their smelting practice, the specificity of ore selection, the consistency of technique points to an inherited tradition, not a freshly created one. Someone, somewhere, at some point before the Vinci archaeological record begins, had already done the work of initial discovery and initial refinement. The Vinci were not at the beginning of this story. They were somewhere in the middle of it. How far from the beginning is a question the evidence cannot yet answer. Iron is not copper. The difference between smelting copper and smelting iron is not a matter of degree. It is a categorical shift in the difficulty of what the human body, working with ancient materials, is being asked to accomplish. Copper smelts at approximately 1085 degrees Celsius. This temperature is achievable with a sustained charcoal fire and a modest air blast from simple bellows. The result, liquid copper, is visually unambiguous. You can see it flow. You know when it has worked. Iron smelting requires sustained temperatures between 1200 and 1500 degrees Celsius. To place a number against something abstract, 1200 degrees Celsius is the temperature at which glass flows as a liquid. It is the surface temperature of volcanic lava in active flow. It is the threshold at which human bone begins to combust. Reaching and sustaining this temperature with clay walls, charcoal fuel, and hand-powered bellows is not a matter of building a bigger fire. It requires a specific combination of furnace geometry, air delivery rate, charcoal grade, and charge management that produces the necessary thermal conditions through an interaction of factors that are individually manageable only if the relationship between them is already understood. The ancient bloomery furnace, the clay shaft furnace that was the primary iron smelting technology across most of the ancient world, is not a simple device. The angle and placement of the tuyeres, the clay tubes through which air entered the furnace, determined the specific pattern of temperature gradients within the furnace interior. The grade of charcoal used affected the rate of heat generation and the carbon chemistry of the resulting iron. The timing of the bloom extraction, the moment at which the partially reduced iron mass was removed from the furnace for working, required reading the behavior of the furnace in real time and responding correctly. Archaeological evidence from multiple ancient bloomery sites shows that the furnaces were built to standardized internal dimensions, consistent across sites in ways that indicate a transmitted specification, not improvised construction. These were not experiments. They were repetitions of a known process. When modern metallurgy students are given access to period-accurate materials, the right clay, the right charcoal, bellows of the appropriate type, and asked to produce workable iron using ancient methods, without any access to modern chemical knowledge, the results are consistently humbling. Most fail to produce workable iron on their first attempt. Many fail on their fifth. The variables are too many, too interactive, too sensitive to small deviations. The process requires a kind of embodied understanding that cannot be acquired from descriptions alone. It has to be learned through direct practice, through repeated failure, through the gradual calibration of attention to the furnace's behavior that only comes from long experience. The ancient smiths who ran these furnaces reliably, at scale, were not doing something primitive. They were doing something extremely sophisticated, and they were doing it without any of the theoretical scaffolding that modern chemistry provides for understanding why the process works. Something in the knowledge chain was more complete, more precise, and more carefully transmitted than the word primitive could ever accommodate. Around 1200 years before the Common Era, the Hittites of ancient Anatolia, the people whose empire stretched across most of what is now Turkey and into the Levant, possessed iron weapons that were categorically superior to the bronze arms of their neighbors. This superiority was not accidental. The Hittites knew it, protected it, and weaponized the knowledge itself. Their royal correspondence reveals iron as a state secret. Access was restricted, export was forbidden, and there are references in Hittite texts to smiths who attempted to share the technology with outsiders being treated as criminals. The iron was not just a weapon. The knowledge of how to make it was a weapon too. This is the part of the story that textbooks correctly report. What they tend to skip is the question that the Hittite evidence raises about its own origins. Because the Hittites, when examined carefully through their own archives, do not look like inventors. They look like guardians. The linguistic evidence is suggestive. The Hittite word for iron and the words for iron in Sumerian, Akkadian, and Proto-Semitic languages all appear to derive from a common root that predates any of these civilizations' written records. Language carries memory that the formal record sometimes loses. When multiple civilizations in a region share a word, when the root is older than any of the cultures currently using it, that word points toward a shared origin, toward something learned from a common source or a common ancestor. The ironworking terminology of the ancient Near East remembers iron from somewhere older than the Hittites, in a linguistic stratum that the archaeology has not yet fully located. At a site in central Turkey called Karmankalehoyuk, excavations have produced iron smelting evidence dated to approximately 2100 BCE, 5 centuries before the Hittites are conventionally credited with developing the technology, in archaeological layers that clearly predate Hittite occupation of the site. This evidence is not widely cited in mainstream accounts of early iron technology. It does not fit cleanly into the standard narrative, and so it sits at the edge of the conversation, carefully documented, not yet integrated into the story that most people hear when they are told about the beginning of the Iron Age. The Hittites guarded knowledge that their own archives suggest they received from somewhere else. They made it a state secret, threatening death to smiths who tried to leave their territory. But a secret is not an invention. A secret is something someone else might find out. And the question that their extraordinary security measures quietly raise the question that the whole Hittite iron story, read carefully, points toward is one that shifts the compass entirely. If the Hittites learned iron smelting from someone before them, then who taught the teachers? In the 1970s, an American anthropologist named Peter Schmidt was working in the highlands of northwestern Tanzania, conducting oral history interviews with elders of the Haya people. The Haya had no reputation, in the academic literature Schmidt had read, for any distinctive metallurgical tradition. They were documented as a farming society, culturally sophisticated, historically complex, but not notable for anything that would have drawn a metallurgical researcher. Schmidt was not there to look for iron technology. He was there to listen to history. The elders spoke, as they always did, about many things about their ancestors, about the customs of earlier generations, about the techniques and traditions of the people who had come before. And in the course of these conversations, as naturally as they might describe farming or weaving, they described how their great-grandfathers had made a particular kind of iron, a special iron, harder than ordinary iron, made in furnaces that were unlike anything Schmidt had seen described in the archaeological record for this region and this period. Schmidt followed the description to the ground. He excavated, guided by the oral map the elders had provided, and he found furnace ruins in locations the elders had indicated. What the excavation revealed was not consistent with the standard picture of ancient African iron technology. The furnaces were sophisticated, preheated air blast systems, structures that forced air through burning coals before it entered the smelting chamber, raising the temperature of the incoming air blast by several hundred degrees, and achieving sustained furnace temperatures of approximately 1400 degrees Celsius. These temperatures were 200 to 300 degrees above what the academic literature considered achievable with ancient bellows technology in this region. And the material produced in these furnaces was not iron. It was carbon steel, high carbon steel, with carbon content sufficient to qualify as a true steel alloy. In the archaeological record, it dates around 1400 to 1500 years before the Common Era. Steel, not iron. Steel, in Tanzania 3,000 years ago. A material that Western industrial metallurgy would not produce consistently and deliberately until the 19th century CE. Schmidt published his findings. The response from the mainstream archaeological community was not dismissal, exactly. It was something quieter, and in some ways more resistant. A silence that acknowledged the findings without integrating them. A scholarly culture that noted the evidence without allowing it to disturb the larger framework. The higher furnaces became a specialized footnote in the literature of African technology studies, rarely cited in the general history of metallurgy, rarely taught in the courses where the history of iron and steel is presented to students. When Schmidt asked the higher elders what they thought of this discovery, whether they found it surprising that their ancestors' technique had preceded the official history of steel by so long, their response was the sentence that stays with you after everything else has been analyzed and categorized and set into context. They said, "Our grandfathers always made it this way." There was no surprise in it, no performance of astonishment for the visiting academic, just the quiet confidence of people who knew their own history, even when the world outside had decided that history wasn't worth recording. Tanzania was not an exception. It was a signal, the first clear note of something much larger that was waiting, in the soil and in the memory of the continent, to be properly heard. There is a silence in the conventional history of metallurgy, where a continent should be. Sub-Saharan Africa, the largest unbroken landmass in the world, inhabited by human beings longer than any other region on Earth. The origin point of the entire human species and everything human beings have ever learned appears in most accounts of ancient metalworking as an absence, a blank, a region where, according to the standard story, iron technology arrived late and was practiced in simple forms until contact with Arab traders and European colonizers introduced more sophisticated methods. This absence is not presented as a gap in knowledge. It is presented as a description of the facts. The geology alone should have made this story suspicious. Sub-Saharan Africa contains some of the most abundant and accessible iron ore deposits on the planet. The Great Lakes region of East Africa, the Nigerian highlands, the Congolese interior, the Zambian copper belt. These are places where iron ore appears at the surface in outcroppings that require no mining knowledge to locate and no deep excavation to access. The ore is simply there, exposed to the air, present in the landscape as an obvious and available material. The people who inhabited these regions for tens of thousands of years before any formal Iron Age, who were not, by any measure, less curious, or less observant, or less capable of systematic experimentation than people anywhere else on Earth, somehow, according to the standard account, never developed a working relationship with this material until it was imported to them. This is not a conclusion. It is a choice, disguised as a conclusion, the product of a scholarly culture that largely did not fund the expeditions that would have looked, and built its absence into a narrative architecture that made the looking seem unnecessary. When archaeologists and anthropologists did look, when they actually went to these regions with shovels and carbon dating equipment, and open questions, what they found was entirely different from the standard story. Iron smelting sites dated to between 2500 and 1500 years before the Common Era appear across sub-Saharan Africa, in a distribution that is not the pattern of a technology arriving from outside. It is the pattern of a technology developing from within. At Termit in Niger, iron smelting evidence appears around 1800 BCE. At multiple sites in the Rwanda and Burundi highlands, sophisticated furnace complexes have been dated to periods that place them among the oldest ironworking sites in the world, competitive with the earliest dates from the Near East. The Nok culture of central Nigeria, a civilization that produced some of the most artistically extraordinary terracotta sculptures ever found anywhere in Africa, was iron smelting by 1500 BCE, in a region the conventional timeline describes as a Stone Age society at that date. The Nok, it should be noted, did not consult the timeline before deciding to smelt iron. They were not aware that they were not supposed to yet. And so, apparently, they simply proceeded. What the Nok sites show, when examined in detail, is not a simple bloomery tradition producing basic iron tools. The furnace remains at Nok sites reflect a level of technical sophistication in furnace construction, in the management of smelting temperatures, in the quality of the iron produced that is inconsistent with a recently initiated practice. The Nok appear not to have been at the beginning of their iron smelting tradition when the archaeological record first captures them. They appear, like the Vinci at the beginning of their copper tradition, to already be well into it, already past the experimental phase, already producing iron reliably, already distributing iron objects across a social network wide enough to leave traces at multiple sites across the central Nigerian plateau. Behind the earliest knock iron there must be an earlier knock iron, or an older tradition from which the knock inherited their technique, one that has not yet been found because it has not yet been looked for with sufficient investment and appropriate methods. This is the recursive quality of the evidence that makes the conventional timeline so difficult to defend once you have looked at it honestly. Every earliest points toward an earlier still. Every origin sits on top of older layers that the record has not yet fully revealed. The African metallurgical tradition is not a late arrival to the global story of human metalworking. It is one of the oldest. And the silence around this fact in the standard accounts of metallurgical history is not a reflection of the evidence. It is a reflection of what the field chose to look for, where it chose to look, and what it decided in advance it would find. Understanding what these African metallurgists were actually doing requires spending some time inside the furnaces they built, not literally, but imaginatively, following the physical logic of the engineering to where it leads. The preheated air blast furnace that Peter Schmidt found in Tanzania was not unique to that site. Variants of the same fundamental design in which air is heated before it enters the smelting chamber, rather than delivered cold from the bellows, have been documented across East Africa, Central Africa, and parts of West Africa, in furnace systems whose construction and operation reflect a sophisticated understanding of the thermodynamics of the process. The principle is this: if you heat the air that your bellows are delivering before it enters the furnace, you gain two things simultaneously. You increase the achievable furnace temperature because the air arrives already carrying thermal energy rather than absorbing it from the charge. And you increase the efficiency of the combustion chemistry because the higher temperature of the incoming air drives the chemical reactions that reduce iron ore to metal toward completion more rapidly and more completely. Both effects compound each other. The result is a system that operates at temperatures previously considered unreachable, with ancient bellows technology, producing iron and steel whose quality is correspondingly higher. This preheating principle, the hot blast, was independently rediscovered by a Scottish engineer named James Beaumont Neilson in 1828 CE and patented as a revolutionary advance in industrial iron production. It transformed the economics of iron smelting in the early 19th century and became a foundational technology of the Industrial Revolution's second phase. Neilson was not aware, when he filed his patent, that the same principle had been in active use across parts of East Africa for 2,000 to 3,000 years. The furnaces that used this principle were not simple. The clay used in their construction was not chosen arbitrarily. It was a specific type of clay, rich in particular minerals, capable of withstanding sustained high temperatures without cracking. In multiple documented sites, the clay was sourced from termite mounds, an observation-based choice that reflects long empirical experience with material properties, because termite mound clay has a specific mineral composition that makes it exceptionally suitable for high-temperature furnace construction. The bellows pipes that delivered heated air were positioned and angled through the furnace walls in ways that maximized the thermal efficiency of the system. The dimensions of the smelting chamber were calculated whether through accumulated oral knowledge or through geometric understanding, or both, to produce specific temperature distributions within the furnace interior. None of this can be improvised. None of it can be arrived at through a single generation's experimentation. This is knowledge that accumulated over time, was tested and refined, and was transmitted from master to apprentice through a system that preserved not just the steps of the process, but the rationale behind each step. The understanding of why this angle of tuyere placement, this grade of clay, this grade of charcoal, and not another. In the Rwanda and Burundi highlands, anthropologists recorded smelting ceremonies in the 20th century that encoded this technical knowledge in ritual form. The sequence of actions performed, the timing of each intervention in the process, the specific materials used at each stage, preserved in sacred ceremony, precisely because ceremony was the most reliable carrier medium available in a world without written records. The ritual was not mysticism decorating a technical process. The ritual was the technical process, wearing the clothing that would keep it alive. Think about what this actually represents. A smelting ceremony that encodes metallurgical knowledge in its sequence and timing is not a primitive conflation of religion and craft. It is an extraordinarily sophisticated solution to a specific and genuine problem. How do you transmit precise technical information through generations of practitioners who have no writing system, no measurement tools, and no chemical vocabulary to describe the variables they are managing? The answer these communities arrived at is, in terms of information theory, elegant embed the information in a form that has independent social value and therefore social protection. A ceremony has authority. It has guardians. It has cultural momentum behind it. People do not casually modify a ceremony the way they might casually modify a recipe. They perform it as it was performed before, because that is what a ceremony is. The precision of the metallurgical information is protected by the very conservatism that makes ritual effective as a cultural institution. The African iron smelting traditions that encoded their knowledge this way were not being religious about a technical activity. They were being methodical about a preservation problem, and their method worked for thousands of years, against disruptions that would have destroyed any purely written record long before the 20th century arrived to document what had been kept. Great Zimbabwe rises from the savanna of southern Africa with the quiet authority of things that were built to last. The massive stone walls, some reaching 11 meters in height, constructed without mortar from carefully fitted granite blocks, were the center of a trading civilization whose network stretched from the interior of southern Africa to the Swahili coast, across the Indian Ocean to Arabia, and onward to India. At its height, between the 11th and 15th centuries of the Common Era, Great Zimbabwe was one of the wealthiest cities in the world, moving gold and ivory and iron through a commercial system of extraordinary geographic reach. The metalwork that passed through that system was extraordinary in its own right. The Shona civilization that built Zimbabwe produced iron wire drawn to gauges that required multiple stages of successive drawing, annealing, and work hardening, a technically demanding process in which the iron is progressively reduced in diameter through dies while being periodically reheated to restore its workability. They produced iron ingots standardized to consistent dimensions and weights, used as a currency that circulated across the entire trading network. They produced gold and iron alloy objects whose surface treatments achieved through controlled oxidation and specific high-temperature finishing processes produced aesthetic effects that were simultaneously practical, conferring specific surface properties on the metal that affected its durability and its behavior under use. Most significantly, they produced a high-phosphorus wrought iron that, like the Delhi pillar, demonstrated exceptional resistance to atmospheric corrosion. This is not coincidence. It is evidence of a metallurgical understanding, whether arrived at independently or through the Indian Ocean trade networks that connected these regions of the relationship between iron's composition and iron's behavior over time. When the first European explorers reached Great Zimbabwe in the 19th century, the metalwork they encountered was described in their official reports as crude, primitive, simple. These words were not technical assessments. They were not produced by materials analysis or by any form of scientific examination of the objects in question. They were produced by men whose intellectual framework had no category for sophisticated African metallurgy, because that framework had been built without consulting any evidence from this part of the world. The word primitive, applied to the metalwork of Great Zimbabwe, was doing political work. It was maintaining a story. It had nothing to do with the objects. When 20th century materials scientists examined surviving pieces from the region, wire-drawn iron artifacts, alloy compositions from smelting sites, surface-treated gold objects, what they found was a body of work that pushed back against the political narrative with the impersonal authority of physical evidence. Wire-drawing ratios that contemporary metallurgists described as difficult to reproduce with modern equipment. Alloy compositions that reflected systematic, deliberate control of the smelting process. Surface treatments whose chemistry indicated an understanding of oxidation-reduction reactions at the metal's surface that the 19th century European visitors, for all their confidence, would not have been able to explain. The word primitive, it turns out, was not a description of the metalwork. It was a description of the vocabulary being used to evaluate it. And that vocabulary, the one that looked at extraordinary technical achievement and saw only the absence of the expected European markers of sophistication, was itself a product of the same framework that built the silence in the standard history. Half a world away, in other workshops and other traditions, other smiths had found other paths to the same impossible heights, and what they built in their furnaces was waiting to be understood by anyone willing to look without the filter already in place. In the year 2006, a team of researchers at the Technical University of Dresden examined a 17th century Damascus sword blade under a scanning electron microscope. Damascus steel, the legendary material prized by warriors across the medieval world, from Persia to Japan, for its extraordinary sharpness, its flexibility, and the distinctive watered pattern of its surface, had been the subject of metallurgical analysis for over 2 centuries at that point. Scientists and blacksmiths had been trying to understand and reproduce it since the late 18th century, with results that were consistently interesting and consistently incomplete. The 2006 examination added something new. Inside the ancient steel, at the nanoscale level visible only through electron microscopy, the Dresden team found carbon nanotubes, cylindrical structures of pure carbon, arranged in specific geometric configurations, woven through the metal's microstructure in patterns that contributed directly to the material's legendary mechanical properties. Carbon nanotubes were first identified by modern science in 1991. The recognition of their existence as a category of matter, their synthesis in a laboratory, their structural characterization, all of this happened in the final years of the 20th century. The steel in which the Dresden researchers found them was made in India, sometime in the 17th century or earlier, using a crucible smelting process whose principles trace back in the Indian archaeological record to at least 300 years before the Common Era. The smiths who made that steel had no knowledge of atomic structure. They had no concept of carbon as an element, no understanding of crystal lattices, no vocabulary for describing what was happening at the nanoscale inside the metal they were working. What they had was a process specific, transmissible, refined across generations, through empirical observation, that produced, as one of its outcomes, the self-assembly of carbon nanotube structures within the iron matrix. They did not know this was what they were doing. They did not need to know. The process knew, and the process was in their hands. This steel is called Wootz. It is produced through a crucible process in which iron and specific carbon-bearing materials are sealed together in a clay crucible and subjected to a precisely controlled heating and slow cooling cycle that allows carbon to dissolve into the iron at specific concentrations, and then, during cooling, to precipitate out in the characteristic banded microstructure, the pattern of carbide networks and iron matrix that gives the material its extraordinary combination of properties. The carbon content of true Wootz steel is between 1 and 2%, the range that defines the category of steel rather than iron or cast iron, and the distribution of that carbon through the metal's microstructure is not random but organized in ways that are still not fully understood into the structures that the Dresden electron microscope revealed. Wootz production in southern India dates to at least 300 BCE and probably significantly earlier. By the time the ancient Indian Ocean trade routes were moving commodities across the known world, Wootz was among the most valued items in the cargo. The Indian Ocean is not an ocean in the way that the Atlantic or the Pacific are oceans vast, undifferentiated, defined primarily by their enormity. It is a structured body of water whose seasonal wind patterns, called monsoons, made it one of the most navigable regions in the ancient world for mariners who understood the system. From May through September, the wind blows reliably from the southwest, driving ships from East Africa and Arabia toward the coasts of India and beyond. From November through March, it reverses, blowing from the northeast and returning those ships to their home ports. The monsoon system is a maritime calendar, and people understood it as such for at least 3,000 years before it appeared in any European navigational record. Wootz steel entered this system early. By 300 BCE, it was being exported from southern Indian port cities to the Persian Gulf, where Arab craftsmen in Damascus received it, worked it further, and distributed it under the name that modern history has attached to it, Damascus steel, into the arsenals of Persia, Rome, and eventually the entire medieval world. The steel moved along these routes for 1,000 years, continuously, in quantities that made it a significant trade commodity. Warriors who could afford it sought it specifically. Rulers who possessed it understood it as a strategic asset. Smiths who worked with it recognized its properties as categorically different from the iron and steel available to them locally. In all that time, across a millennium of distribution and analysis, no one outside the Indian crucible smelting tradition ever successfully replicated the process. This is one of the earliest and clearest examples of what modern technology economics calls a black box, a product so sophisticated that its reverse engineering from inspection alone is not merely difficult, but effectively impossible. Buyers could examine Damascus blades in exhaustive detail, could measure their hardness and test their edge retention, and observe their surface patterns, and could not from this observation reconstruct the crucible chemistry that produced them. The knowledge did not travel with the product. It stayed in the workshops, in the hands and habits of the Smith families, who had maintained and refined it across generations. When European colonial administrators arrived in South India in the 18th century and attempted to document Wootz production for commercial purposes, they encountered something that should have been recognized as a profound insight about the nature of technical knowledge, but was instead treated as frustrating incompetence. The Smiths, who still practiced the Wootz tradition, could not fully describe their own process. They could demonstrate it. They could produce the result. But asked to articulate the specific variables, the exact temperature, the exact timing, the exact composition of the carbon-bearing additive, the exact cooling rate, they could not provide systematic answers. The knowledge was not in their words, it was in their hands, in their eyes reading the color of the crucible. In the particular way, the material felt and behaved under specific conditions that only the accumulated experience of a lifetime could read correctly. This is not ignorance. This is a different architecture of knowledge, one that Western scientific culture was not equipped to recognize or respect, and one that would prove, within a century, to be fatally fragile. In the year 700 before the Common Era, China was producing cast iron. Let that settle for a moment. 700 years before the Common Era, cast iron, the material whose production requires furnace temperatures above 1150 degrees Celsius, and precise control of carbon chemistry during both the smelting and the solidification phases, was being inerty. Made in China during the early Zhou dynasty, in a form sophisticated enough to be used for agricultural tools and weapons in routine manufacture. The Industrial Revolution in Europe, the transformation of human civilization between approximately 1760 and 1840 that created the modern world, was powered in significant part by cast iron. The steam engines that drove the factories were made of it. The rails that crossed the continents were made of it. The Iron Bridge in Shropshire, England, completed in 1779 and celebrated as one of the greatest engineering achievements of its era, was made of it. Cast iron made the modern world possible. China had been making it for 1,200 years before the Iron Bridge opened. The Chinese achievement was not accidental. The metallurgical tradition that produced cast iron during the Zhou dynasty was built on generations of furnace engineering that developed in parallel with, but independently from, the Near Eastern and European traditions, a specific set of solutions to the challenge of sustained high-temperature iron processing. The Chinese developed multi-chamber blast furnaces with internal geometries that concentrated and sustained the necessary thermal conditions. They developed bellows systems made from leather that could deliver the high-pressure, high-volume airflows the process required. And most significantly, in a development that stands as one of the most remarkable achievements in the entire history of pre-modern technology, they developed what modern metallurgists call decarburization, a controlled post-smelting process in which the carbon content of cast iron could be deliberately reduced by reheating the material in a specific atmospheric environment, converting it into wrought iron or steel as required by the application. This is not simply making iron. This is managing the chemistry of iron in both directions. Adding carbon through the smelting process, removing it through subsequent controlled oxidation to produce specific materials for specific purposes. It is, in functional terms, a proto-scientific understanding of iron-carbon chemistry, achieved through empirical observation and systematic practice 6 centuries before Christ. The theoretical framework that explains why it works would not be assembled by Western chemistry for another 2.5 millennia. But the Chinese achievement goes even further than the cast iron milestone. By the 2nd century of the Common Era, Chinese metallurgists had developed a process that modern materials science calls co-fusion. The deliberate combination of cast iron and wrought iron in a single furnace charge, allowing the carbon-rich cast iron to diffuse carbon into the carbon-poor wrought iron during a controlled heating cycle, and produce steel with specific, targeted properties at the interface. This process is a precursor, in its essential chemistry, to the co-fusion steelmaking that appeared in medieval Europe as a significant advance. In China, it was routine production by the time of the Han Dynasty. The Chinese government, across multiple dynasties, recognized the strategic significance of this metallurgical capability and organized it as a state enterprise. Iron production was not left to individual craftspeople but was administered by imperial ministries, with production targets, quality standards, and resource allocation managed at a national scale. This is not the picture of a civilization accidentally stumbling upon metallurgical results it did not fully understand. This is a civilization that understood its metallurgical capabilities well enough to organize them as a foundational industrial system, and that did so more than 1,000 years before Europe achieved comparable industrial organization of iron production. Most discussions of ancient Asian metallurgy keep their attention on the major civilizations: India, China, the broader Near Eastern sphere. The islands of Southeast Asia, the Philippines, Borneo, the Indonesian archipelago appear in such discussions rarely, if at all, as though the maritime geography that separated these communities from the Asian mainland also separated them from the relevant human history. The physical evidence disagreed, at least as far back as 500 BCE. At that date, iron smelting was already operational in island Southeast Asia, specifically documented in archaeological sites in the Philippines and in several locations across the Indonesian islands, in a form sophisticated enough to produce tools and blades whose quality would later astonish the first European navigators to encounter them. No clear import route for this technology has been identified at those dates. No evidence of significant contact with mainland Asian metallurgical traditions at the relevant time period has been demonstrated. The island communities who were smelting iron in 500 BCE had no visible connection, in the archaeological record, to the traditions in China or India whose own iron technology was developing simultaneously or slightly earlier. Yet the knowledge was present. The furnaces were working. The blades were made. When Spanish expeditionaries arrived in the Philippines in the 16th century CE, their accounts describe Filipino iron, with a particular quality of attention that reveals something significant. They were not encountering primitive products that they could easily improve upon or replace. They were encountering blades, specifically the steel weapons produced by Filipino smithing traditions, that they immediately recognized as superior to what they carried. And they sought to obtain Filipino iron rather than displace it. A maritime force that had conquered the Aztec and Inca empires, that carried some of the finest European steel weapons of the 16th century, found the island metallurgy not inferior, but competitive. Either iron smelting was independently invented in island Southeast Asia, a fourth independent origin, in addition to the Balkans, Africa, and India, or there was a maritime knowledge network in the ancient world, connecting these island communities to a metallurgical tradition we have not yet identified. Both possibilities have profound implications. One suggests that the cognitive and experimental prerequisites for iron technology are more widely distributed in the human species than the standard story allows. The other suggests that people were moving across open ocean, carrying technical knowledge as cargo, long before the documented voyages of exploration that textbooks treat as the beginning of global connectivity. Neither option fits comfortably in the conventional timeline. Both options are consistent with the physical evidence that the ground has kept. In the coastal desert of northern Peru, in the dry tombs of the Moche civilization that flourished between approximately 100 and 800 of the Common Era, archaeologists have found objects made of platinum. Not gold decorated with platinum, not gold that happens to contain trace amounts of a platinum group element. Objects in which platinum and gold have been deliberately combined into a stable, worked alloy, beaten, shaped, and finished into nose ornaments, ceremonial pendants, and ritual implements, with a precision and aesthetic sophistication that reflects generations of intentional craft. Platinum melts at 1768 degrees Celsius. This temperature is not achievable in any furnace built before the industrial age. It requires electric arc furnaces or specialized induction heating that belongs entirely to the technology of the 20th century. The Moche had clay furnaces, charcoal, and the wind off the Pacific. The Moche were making platinum objects in the 1st century of the Common Era. The technique they used is called sintering. Rather than melting the platinum, since melting was not possible, they obtained platinum in powdered or granular form, deposited it onto a gold substrate, and subjected the composite to repeated cycles of heating and working, in which the platinum particles were pressed into intimate contact with the gold surface and fused to it through diffusion bonding at temperatures high enough to achieve atomic scale joining without reaching the melting point of either metal. This is a subtle, technically demanding process that requires precise control of temperature, time, and mechanical pressure across multiple processing cycles. It requires an understanding, whether theoretical or empirical, of the conditions under which metal atoms will migrate across a surface boundary and create a permanent bond without the material flowing as a liquid. Modern jewelers who work with platinum use a version of this exact technique. It was not a standard industrial process in Western jewelry manufacture until the late 19th century. The Moche were using it 1800 years earlier, on the other side of the world, without any contact with any old world metallurgical tradition, and producing objects of sufficient technical quality that the first scientific analyses of Moche platinum work, conducted in the 20th century, required electron microscopy to fully characterize. The Andean relationship with metal was not the old world's relationship with metal. Where the metallurgical traditions of Europe, the Near East, Africa, and Asia focused primarily on iron and bronze materials, whose value was primarily functional, whose properties of hardness and edge retention made them useful for weapons and tools. The Andean civilizations worked primarily in gold, silver, copper, platinum, and the alloys between them, and they valued these materials not as utilities but as cosmic substances. Gold was the sweat of the sun. Silver was the tears of the moon. Metal was not tool material. Metal was the concentrated essence of divine reality, given material form. This cosmological framework, which sounds to the modern ear like poetic mysticism, was functionally a research program. When the goal is spiritual precision rather than practical utility, the experimental space expands in unexpected directions. The Moche were not sintering platinum because they needed a harder material for tools. They were sintering platinum because they were trying to capture and work with a substance that had specific cosmological properties, and the technical demands of doing so drove them towards solutions that utilitarian metallurgy would never have motivated. High in the Bolivian plateau, at altitudes where the thin air makes sustained physical labor genuinely difficult, the Tiwanaku civilization maintained a bronze production tradition that operated from roughly 300 BCE until the civilization's collapse around 1000 CE, more than 1,000 years of systematic, large-scale metal production in one of the most challenging environments on Earth. What makes the Tiwanaku bronze remarkable is not simply that it was produced consistently over this period. What makes it remarkable is how it was produced. Analysis of bronze objects from Tiwanaku sites, objects recovered from ceremonial contexts, from domestic deposits, from the trading sites where Tiwanaku goods circulated across the high Andes, reveals something that should not be possible in a civilization without a writing system and without a formal system of measurement. The bronze was made to specification, not to an approximate specification, not to a rough standard that varied significantly across sites and across centuries, but to two precise alloy ratios, copper and tin, mixed at 90 parts to 10 parts, and at 95 parts to 5 parts that correspond to specific intended applications. The 90-to-10 ratio produces a harder, more brittle bronze appropriate for tools requiring a sharp edge. The 95-to-5 ratio produces a tougher, more ductile material appropriate for objects that need to flex without fracturing. A modern manufacturer maintaining these two specifications across a geographically distributed production network would use written recipes, standardized measuring equipment, quality control protocols, and trained supervisors who understood the chemical basis of the standards they were maintaining. The Tiwanaku had none of these in any form that has survived in the archaeological record. What they had, and what must have been doing, the work of all these systems simultaneously, was a tradition of knowledge transmission so precise and so reliable that it maintained the same alloy ratios across hundreds of years, and thousands of square kilometers of mountain terrain without leaving a single written record of how it was done. The answer, as it so often is in the ancient world, appears to have been embedded in ritual. The ceremonies that surrounded metal production in Andean cultures were not decorations applied to a technical process. They were the carriers of the technical process itself. The specific sequence of actions in the smelting ritual encoded the timing of each stage. The dimensions of sacred objects used in the ceremony encoded the ratios literally in the proportions of the objects. The recipe for the alloy was physically instantiated in a form that could be reproduced without any act of measurement, simply by matching the established sacred form. The Tiwanaku metallurgy was, in a very precise sense, their mathematics a system for transmitting exact quantitative information through a culture that had chosen not to write it down. When Spanish conquistadors arrived on the Pacific coast of South America in the 16th century, they encountered, in the gold objects of the coastal peoples, an unfamiliar metal that appeared in small quantities, mixed into the gold that behaved in strange ways. It was greyish-white where gold was yellow. It would not melt. It was harder than gold and resisted the tools the Spanish used to assess gold's purity. They called it Platina del Pinto, little silver of the Pinto River, and they regarded it not as a precious material, but as a contaminant, an inferior substance that degraded the quality of the gold it was found in. In documented cases, they threw it back into the rivers. In other cases, they melted the objects entirely, recovering the gold and discarding whatever they could not use. What they were discarding was the result of 3 centuries of systematic experimental refinement by the Tumaco La Tolita culture of coastal Colombia and Ecuador, who had been working with platinum sintering, the same technique used by the Moche, arriving apparently independently or through interregional contact along the Pacific coast from approximately 300 BCE to 200 CE. The Tumaco La Tolita objects were not accidents. When materials scientists analyzed a range of them in the 1970s, the results showed something that changed the conversation about pre-Columbian technical sophistication permanently. The sintering quality of the platinum gold work improved measurably and consistently across the chronological sequence of the objects. The earliest pieces showed a specific degree of bonding quality. The middle period pieces showed a higher degree. The latest pieces showed the highest degree, approaching the technical ceiling of what the sintering process can achieve without more extreme equipment. This is not the pattern of lucky improvisation or of occasional talented individuals producing unusual results. This is the pattern of a sustained, intergenerational research program, each generation receiving the knowledge of the previous generation, practicing it, refining it slightly, and passing on a marginally improved version to the generation following. This is how science works when it does not call itself science. This is what progress looks like when it is encoded in the hands of craftspeople rather than in the pages of journals. The Spanish conquistadors, throwing Platina del Pinto into the rivers of coastal Colombia, were discarding 3 centuries of material science conducted by people who had no name for what they were doing. The loss was not unique. It was the leading edge of something much larger, a global pattern of erasure that would be examined, eventually with grief and without adequate explanation. Before that examination, however, the evidence demands a different question. Given everything that has been observed across Africa, India, China, Southeast Asia, and now the Americas, how did these civilizations, separated by oceans, uncommunicating through any channel the official history acknowledges, arrive at solutions of equivalent sophistication at roughly equivalent periods in human history. Was this convergence? Was it contact? Or was it something in between, a network so subtle and so distributed that its traces are everywhere and nowhere at once? There are two explanations available when human beings in different parts of the world, without any documented contact, develop the same complex technology at roughly the same period in history. The first is convergent invention, the idea that the same problem, pressing upon human minds with similar cognitive architecture and similar environmental pressures, produces the same solution independently in multiple locations. The second is cultural diffusion, the idea that the knowledge traveled through trade or migration or some form of contact that the historical record has not clearly preserved, from an original source to multiple destinations. Both explanations are real. Both have been demonstrated in documented cases. The question is not which one is theoretically possible, but which one is the more plausible account of specific observed evidence. For simple technologies, fire-making, the fashioning of stone tools, the production of basic pottery, convergent invention is entirely credible. These are technologies whose underlying principles are accessible to direct observation by any curious person with time and attention. The properties of fire, the fracture patterns of flint, the plastic behavior of wet clay heated to dryness, these are available to any human being who looks and experiments. Independent discovery, multiple times, in multiple locations, is not just possible, but expected, and the archaeological record confirms it. Fire-making techniques, stone tool traditions, ceramic production appear independently across the inhabited world at various dates, in forms that reflect local materials and local preferences, with no evident single origin that diffused outward. But high-carbon steel production is not pottery. Platinum sintering is not fire-making. Preheated air blast furnaces operating at 1400 degrees Celsius are not flint knapping. These technologies require knowledge that is not accessible to direct observation. Knowledge of the specific interaction between temperature, carbon content, cooling rate, and the resulting microstructure of the metal. Knowledge of the conditions under which platinum particles will fuse to a gold substrate without the material flowing. Knowledge of how to build a furnace that concentrates and sustains temperatures that are not intuitive, that cannot be stumbled upon, that require a specific sequence of design decisions whose rationale is not apparent from the outside. The complexity threshold matters. Below a certain threshold of technical complexity, independent invention is plausible. Above that threshold, the plausibility decreases sharply. The technologies appearing simultaneously in Africa, India, China, Southeast Asia, and the Americas sit well above that threshold. They require the kind of procedural knowledge chain that, once established, is genuinely difficult to re-establish from scratch after it has been broken, as modern reconstruction attempts have consistently demonstrated. The easier explanation, at that level of complexity, is transmission. Someone taught someone else. The knowledge traveled. What the evidence cannot yet show is exactly how. In 1992, a German forensic scientist named Svetlana Balabanova published a paper in a respected scientific journal reporting the results of chemical analysis performed on mummified tissues from ancient Egypt. Among the substances she detected in these tissues from mummies dated to approximately 1000 BCE were cocaine and tobacco residues. Cocaine is derived from the coca plant, native exclusively to South America. Tobacco comes from Nicotiana species, also native exclusively to the Americas. In 1000 BCE, there is no accepted historical framework that places any contact between Egypt and the Americas. The plants simply should not have been present in those bodies. The response from the archaeological community was skeptical in the specific way that inconvenient findings draw skepticism. The methodology was questioned, the contamination hypothesis was raised, the analysis was questioned without being repeated by the skeptics who questioned it. But subsequent independent analyses, conducted by different laboratories, using different samples from the same collections and from other Egyptian collections, confirmed the presence of the substances. The finding was not a laboratory artifact. The cocaine and tobacco were there. This does not mean that Egyptians sailed to South America. It means that goods originating in the Americas were finding their way to Egypt by some route, through some mechanism, before 1000 BCE. It means that the trade networks of the ancient world were more extensive and more capable of moving commodities across vast distances than the framework currently acknowledges. It means that the idea of isolated, disconnected, ancient civilizations developing in parallel without any contact is not a conclusion from evidence. It is an assumption that the evidence is quietly but repeatedly contradicting. The ancient world had several maritime systems capable of moving people and goods over long distances. The Lapita culture of the Pacific, the ancestral population from which the Polynesian peoples descended, was navigating open ocean across thousands of kilometers before 1000 BCE, using star maps, wave-reading techniques, and navigational knowledge passed through oral tradition that allowed precise positioning without any instrument. They colonized islands separated from the nearest landmass by more than 3,000 kilometers of open water. The Indian Ocean monsoon system, understood and exploited by East African, Arabian, Indian, and Southeast Asian mariners from at least 1000 BCE, created a reliable annual circuit that connected the coasts of 4 continents in a seasonal loop of trade and contact. The Norse presence in North America, confirmed by the Lanceau Meadows site in Newfoundland, demonstrates that transatlantic crossing was technically achievable long before any European account claims it. None of these systems operated in isolation from the others. They were nodes in a global network of maritime movement whose full extent and whose role in carrying technical knowledge across its routes has barely been surveyed. The Phoenicians, whose maritime trading network extended across the entire Mediterranean and into the Atlantic by roughly 1000 BCE, are one of the most underappreciated conduits of technical knowledge in the ancient world. Their routes connected the silver mines of Iberia to the workshops of the Near East. Tin ingots with isotopic signatures matching British ore deposits have been found at Phoenician trading sites, confirming connections that extended from the Levant to the far northwest of Europe. What moved along these routes was not only cargo. Metalworkers travelled with their products, or sent skilled representatives. The smith who accompanied a cargo of specialized metal to a distant port left behind not just the material, but fragments of the knowledge framework within which the material existed, partial descriptions, demonstrated properties, contextual knowledge of use and preparation that gradually seeped into the receiving culture's own practice. Repeated across hundreds of voyages and thousands of years, this process of partial, incremental knowledge transmission is a plausible mechanism for the distribution of technical understanding that does not appear fully formed in any single archaeological record, but whose traces show up across multiple cultures at roughly equivalent periods. The knowledge did not need to travel completely or instantaneously. It needed only to travel partially, repeatedly, and in enough different directions that its core principles could be independently reconstructed from multiple partial inputs. This is how technical knowledge spreads in the modern world too, through professional conferences and published papers, and casual conversations between practitioners, and the ancient world had its own equivalents of all. 3. Metal leaves a record of its origins that the human beings who made it cannot erase. Every iron ore deposit on Earth has a specific isotopic signature, a ratio of particular iron isotopes that reflects the geological history of that deposit, distinguishing it from deposits elsewhere in the world with the precision of a fingerprint. When an iron object is smelted, it inherits the isotopic signature of its ore source. That signature survives in the finished metal. And, because the analytical techniques for reading these signatures have become precise enough to distinguish between ore deposits separated by hundreds of kilometers, archaeologists can now, in principle, trace the geographic origins of ancient metal objects with a specificity that would have seemed impossible a generation ago. What this technique has revealed, in the sites where it has been applied carefully, is a picture of metal movement in the ancient world that is far more extensive than the standard account allows. Bronze Age, Mediterranean, shipwrecks the cargo vessels that sank in the deep waters off Cyprus and Turkey, and the Levantine coast during the 2nd millennium BCE contained tin ingots whose isotopic signatures have been traced to ore deposits in Britain, in Brittany, and in Sardinia. These ingots were moving across the entire length of the Mediterranean and into the Atlantic before 1200 BCE, as bulk commodities in a trade network that connected the British Isles to the Levantine coast in a single, organized commercial system. The distances involved are immense. The logistics required are sophisticated. The standard image of Bronze Age trade as a system of local exchange and occasional long-range contact does not accommodate this evidence. The evidence describes a global network. In sub-Saharan Africa, iron objects recovered from trading sites carry isotopic signatures from ore deposits, hundreds of kilometers from where the objects were found, meaning that finished iron goods were being distributed across the continent through a commercial network operating long before the official Iron Age of the region begins. The network predates the Standard story by centuries, and from several pre-Columbian North American archaeological sites securely dated to periods before any acknowledged European contact, iron objects have been recovered whose isotopic signatures are inconsistent with any known American ore deposit. The signatures match deposits in the Old World more closely than they match anything in North America. This finding is treated with great caution by the researchers who have reported it, and appropriately so. Extraordinary claims require extraordinary evidence, and the evidence here is suggestive rather than conclusive. But the puzzle it poses is genuine, and it has not been resolved. The simplest explanation, that these objects contain iron that arrived from outside the Americas, is not the most comfortable explanation. But comfort has never been a reliable guide to what is actually true. The web is not fully visible. Its threads are scattered across the seafloor and the soil of excavation sites and the spectroscopic databases of materials science laboratories. But enough of them have been found to establish that the isolation of the ancient world, the fundamental assumption that allows the impossibilities of ancient metallurgy to be explained away as independent accidents, is itself the thing that needs to be explained away. The question is no longer whether knowledge was moving between civilizations across distances that should have been barriers. The question is, how, and through whom, and at what cost, and what happened when that movement was interrupted. There is no single villain in this story. No committee that met in secret to decide which evidence would reach the public and which would be buried. No authority that issued instructions to discount the metallurgical achievements of African or Asian civilizations. What there is, instead, is something more ordinary and in many ways more resistant to correction. A self-reinforcing structure of institutional knowledge that treats its own assumptions as facts and treats evidence that challenges those assumptions as a problem to be resolved rather than a signal to be followed. Academic knowledge operates through a system of peer review. Before a paper is published in a scientific or historical journal, it is evaluated by other researchers working in the same field, people who have expertise in the relevant subject matter and can assess the quality of the methodology and the validity of the claims. This system exists for good reasons. It filters out bad methodology, catches errors, prevents the dissemination of poorly supported conclusions. It is, in principle, the correct way to manage the integrity of a knowledge system. But the system has a structural feature that creates predictable distortions. The reviewers who evaluate a paper are, necessarily, people who have built their careers and their reputations within the existing framework. Their expertise is defined by the framework. Their training was organized around its assumptions. When they encounter a paper that presents evidence contradicting those assumptions, they are not neutral evaluators. They are people for whom the contradiction represents, at some level, a challenge to the framework that their careers were built on understanding and applying. The philosopher of science, Thomas Kuhn, described this dynamic with precision in his landmark 1962 work. Scientific fields do not advance by smoothly incorporating new evidence. They advance through periodic, often painful ruptures, paradigm shifts, in which accumulated anomalous evidence eventually overwhelms the resistance of the existing framework and forces a fundamental reconceptualization. But between these shifts, the field is in what Kuhn called a normal science phase, a period in which the framework is not seriously questioned, in which anomalous evidence is treated as a problem with the evidence rather than a problem with the framework, and in which the community of researchers actively, if unconsciously, works to preserve the coherence of the system it has inherited. Archaeometallurgy has been in normal science phase, relative to the evidence discussed in this documentary, for most of the 20th century and the early 21st. The treatment of Peter Schmidt's Tanzania findings is illustrative. When Schmidt submitted his initial papers on the preheated air blast furnaces and the carbon steel dates to major journals in the late 1970s, the papers were rejected. The grounds cited were methodological concerns about dating accuracy and questions about the interpretation of the furnace evidence. These concerns were not baseless. Archaeological dating always carries uncertainty, and unusual findings require rigorous methodology. But the level of scrutiny applied to Schmidt's findings exceeded what was routinely applied to findings that confirmed the existing picture. When the papers eventually appeared in lower-profile venues, they circulated in the specialized literature of African studies without penetrating the mainstream accounts of metallurgical history. Today, 3 decades later, the story of Tanzanian carbon steel still does not appear in the standard textbook accounts of when and where steel was first produced. The career of Cyril Stanley Smith occupies a different position in this history, but tells a related story. Smith was one of the great metallurgical historians of the 20th century, a trained materials scientist who brought the tools of modern technical analysis to the history of ancient metalwork and changed the understanding of cosm, multiple specific traditions, through his meticulous scholarship. In his later years, having spent decades examining the physical evidence from multiple ancient metallurgical traditions, he reached a conclusion that the mainstream of his field was not ready to hear. The conventional chronology of steel development was substantially wrong, and the evidence for sophisticated metallurgical knowledge in pre-industrial, non-European civilizations was being systematically undervalued. He published these views, he was cited, he was respected, and the field moved on without him, as though he had described the view from a window that no one else was looking through. The story of Wootz steel in India is the most precisely documented case of deliberate knowledge destruction in the history of metallurgy, and it deserves to be understood in its full specificity, rather than in the abstracted language that softens what actually happened. By the early 19th century, Wootz production in southern India was concentrated in a small number of regional craft communities, hereditary smelter families in Andhra Pradesh and Tamil Nadu, who maintained the knowledge of the crucible process across generations. Through the master-apprentice transmission, that is the only channel through which embodied knowledge can reliably travel. The tradition was ancient, the practitioners were skilled, and the steel they produced was, as materials science analysis would later confirm, among the most sophisticated metalwork that had existed on Earth up to that point. The British East India Company observed the Wootz industry through 2 lenses simultaneously. The first was commercial. Indian steel competed with British iron production in markets where the company had interests. The second was strategic. High-quality steel in the hands of Indian metalworkers was a potential resource for resistance movements against British authority. Both lenses reached the same conclusion. The Wootz industry needed to be suppressed. The suppression was accomplished not through a single dramatic decree, but through the layered application of ordinary commercial and administrative power. Prohibitive taxes were placed on the charcoal that the traditional smelting process required charcoal sourced from specific wood types, prepared in specific ways, whose specific combustion properties were inseparable from the quality of the steel the process produced. British iron was introduced to Indian markets at prices that individual artisan smiths could not compete with at scale. In several documented cases, administrative pressure was applied directly to prevent the training of new apprentices. By 1850, the Wootz tradition had effectively ended. The last practitioners died without adequate replacements. The knowledge chain, which had transmitted itself unbroken across more than 2,000 years, broke. It did not break because it had been superseded. No superior steel technology replaced Wootz. The Damascus blades that Wootz produced have not been matched in their specific combination of properties by anything made since. The knowledge died because an external force, administrative, commercial, and ultimately indifferent to the value of what it was destroying, removed the conditions that its transmission required. What ended was not an inferior tradition meeting a superior one. What ended was one of the greatest technical achievements in human history, killed not by progress, but by policy. Not all knowledge dies violently. Some of it simply dissolves in the quiet aftermath of civilizational disruption. Not targeted, not suppressed, just orphaned. The people who could have continued it were gone before they could finish the transmission. The philosopher Michael Polanyi described a category of human knowledge that he called tacit knowledge, the category of things that we know how to do but cannot fully articulate in words. Tacit knowledge is the majority of what skilled practitioners in any craft actually know. It is the feeling in the hands that tells the experienced smith when the metal is at the right temperature for working. It is the color of the flame that indicates the furnace has reached the specific thermal condition the process requires. It is the sound of the bellows, the smell of the charge, the texture of the slag, the entire sensory landscape of a technical process that cannot be captured in a list of instructions because it lives in the body, in the accumulated experience of years of practice that calibrates the practitioner's nervous system to the specific demands of the work. This tacit dimension of metallurgical craft knowledge cannot be transmitted through writing. It cannot be transmitted through observation alone. It requires the patient process of side-by-side practice in which the apprentice's sensory responses are gradually calibrated against the master's standard, in which the apprentice learns not just what to do, but how the correct execution feels, sounds, and looks in real time under the specific conditions of the actual process. This transmission requires time and proximity, and the continued existence of both master and apprentice in a stable enough environment to complete it. When a civilization is disrupted quickly enough through conquest, through epidemic, through climate catastrophe that forces migration on a timescale that tears the community apart before the transmission is complete, the tacit knowledge dies with the masters, even when the apprentices survive. The Celtic ironsmithing tradition of pre-Roman Gaul is the most thoroughly studied case. Materials analysis of pre-Roman Celtic iron, the blades and tools produced by the Latine culture in the centuries before Julius Caesar's campaigns in Gaul, shows a technical sophistication that in several respects exceeded contemporary Roman iron production. The pattern-welded construction of many Celtic blades, the specific alloy compositions, the heat treatment processes evidenced in the microstructure of surviving objects. These reflect a tradition that had achieved things Roman metallurgy had not. The Latine smiths worked in a specific, regionally distinctive tradition that was organized around the individual workshop, the master smith's personal expertise, and the long apprenticeship through which that expertise was transmitted. Their blades were not standardized products. They were individual achievements, each one reflecting the specific knowledge and judgment of the practitioner who made it. The pattern welding technique, the twisting and forge welding of iron bars with different carbon contents, drawing them out and folding them into composite structures with targeted mechanical properties, required a level of process control that only years of practice could calibrate. No two blades were identical, because no two applications of the technique were identical. The variation was controlled variation, guided by an experienced practitioner's real-time judgment about how the metal was responding. After the Roman conquest, this tradition stopped, not gradually, not slowly, not by evolving into something better. The specific techniques of Celtic iron production essentially disappear from the archaeological record within a generation of Roman occupation. They were absorbed into Roman industrial production, which was organized differently, optimized for different goals, and managed by people who valued output over the subtleties of craft. The Celtic masters were dispersed. The apprentice networks were broken. The tacit knowledge found no new hands to live in. And because it could not be written down, it left no record of what it had been, only objects which later generations could examine and partially reverse engineer, arriving at partial descriptions of techniques they could no longer fully reproduce. This is not conspiracy. This is the ordinary catastrophe of knowledge that has no backup knowledge that exists only in living bodies and in the relationships between those bodies. And that dies whenever those bodies and those relationships are disrupted faster than new ones can form. The same catastrophe, in different forms and at different scales, has been playing out across every civilization examined in this documentary. And the sum of all those losses is what the modern world actually inherited from the ancient one: a partial map, a broken lattice, a set of achievements visible in the objects but separated from the knowledge that made them possible. For more than 200 years, some of the most skilled practitioners of metalworking in the world have been attempting to reproduce Damascus steel to produce, using traditional crucible methods and traditional materials, a steel whose microstructure matches the authentic material. the characteristic carbide banding, the surface pattern, and now that we know to look for them, the carbon nanotube structures that the 2006 Dresden analysis revealed at the nanoscale. The attempt has never fully succeeded. This is not for lack of effort, intelligence, or resources. The effort has been substantial. The intelligence applied to the problem has included some of the finest materials scientists of the past century. The resources available, modern analytical equipment that can characterize the original material at the atomic level, exceed by several orders of magnitude anything available to the Indian Crucible smiths who produced the pass. Authentic material. And yet the gap persists. John Verhoeven, a metallurgist at Iowa State University, spent years attempting to reproduce the Wootz microstructure using traditional processing methods. His work, conducted collaboratively with bladesmith Alfred Pendray, came closer than any previous attempt, producing steels that showed some of the characteristic banding and some of the mechanical properties of authentic Damascus material, but they could not do it consistently. The specific carbide network that defines the authentic material, and that is produced by the specific combination of ore chemistry, crucible chemistry, heating rate, peak temperature, and cooling rate that the original Indian smiths used, has proven to be a target that modern science can describe precisely and hit only approximately. The reason is not the absence of information about the material. Modern science knows, at an extraordinary level of detail, exactly what Damascus steel is. The compositions have been measured. The microstructures have been mapped. The mechanical properties have been characterized. The carbon nanotube content has been identified and described. The explanation of why the nanotube structures form, which involves specific carbide-forming elements in the ore chemistry, acting as catalysts for nanotube nucleation during the cooling phase, has been worked out. The material is understood. What is not understood is the process. Not the theoretical process, the set of physical and chemical events that produces the material, but the practical process, the specific set of actions, in the specific sequence, with the specific materials, under the specific conditions, that an ancient Indian smith in the 3rd century BCE would have performed, using his hands and his eyes and the embodied knowledge of a tradition that was thousands of years old to produce the result. That knowledge, the tacit dimension of the process, the sensory landscape that told the smith when each stage was complete and what the next stage required, is gone. It died with the last generation of Wootz practitioners sometime in the mid-19th century and was not adequately recorded before it went. The modern researchers who work on this problem describe the experience with a consistency that reveals its depth. They can get close. They can make steel that approaches Damascus in quality, using modern analytical equipment to manage the variables that the ancient smiths managed through sensory experience. But to make it the ancient way, using only the materials and equipment the original practitioners had, relying on observation and judgment rather than instruments, with nothing in the process that those practitioners would not have recognized, and to arrive reliably at the authentic result, this remains beyond reach. The gap between what we know about the material and our ability to reproduce it the old way is a direct measure of how much the tacit knowledge actually contained that the theoretical description does not. The Damascus steel reconstruction problem is not unique. It is one item in a catalogue of ancient metallurgical achievements that modern science has analyzed, described, and been unable to reliably reproduce through traditional means. The catalogue is longer than most people realize, and each entry in it carries its own particular flavor of technical impossibility. Consider the Lycurgus cup, a Roman cage cup dating to the 4th century of the Common Era, currently held in the British Museum. The cup is made of a dichroic glass, a glass that appears green in reflected light and glowing red-purple when illuminated from behind, because the glass contains suspended nanoparticles of silver and gold in a specific colloidal distribution that produces optical effects through plasmon resonance at different wavelengths of light. The nanoscale distribution of these particles typically between 50 and 100 nanometers in diameter, is precise enough that modern attempts to replicate the optical effect require controlled conditions and instruments that were not available to the Roman craftsmen who made the original. How those craftsmen achieved this result, whether by accident, by systematic experimentation, or by some other means, has not been established. The techniques of ancient Roman glassworking are reasonably well documented. None of them obviously leads to this outcome. The nanotechnology in the Lycurgus cup was not discovered by modern science until 1990. It was produced by Roman craftsmen in the 4th century. Between those two facts, the cup sits in its glass case in the British Museum, changing colour with the light, carrying a question that polite exhibition labels do not ask. Consider Roman orichalcum, the golden-hued alloy, described in ancient sources with a reverence that suggests it was both rare and visually extraordinary, associated with legendary Atlantis by Plato, and with precious metalwork in multiple Roman and Greek texts. Several ingots of a material consistent with the ancient descriptions were recovered from a Roman shipwreck off the coast of Sicily in 2015. Analysis shows the material to be a zinc-rich brass, but with specific trace element compositions and a surface treatment whose production method has not been fully reconstructed. The visual effect, a color and luminosity that contemporaries distinguished from ordinary brass and treated as a distinct and superior material, depended on something in the processing that current analysis can characterize but not reproduce with full confidence. Consider the meteoritic ironwork of the pre-contact North American cultures of the Great Plains and the Upper Midwest, who had access to meteorite iron in the form of the Campo del Cielo, Gibeon, and Canyon Diablo meteorite fields. These cultures were working nickel-iron alloy from meteoritic sources material, whose composition varies significantly between individual meteorite pieces into ornamental and ritual objects, whose analyzed compositions show targeted alloy ranges that exceed what random selection from available meteorite pieces would produce. This implies an ability to assess the nickel content of meteorite iron, to distinguish higher nickel from lower nickel pieces through some sensory or empirical test, and to preferentially select material meeting specific compositional requirements. The specific test or method by which they did this has not been identified. Each of these cases represents a different facet of the same underlying reality. Ancient craftspeople routinely produced results at a technical level that modern science can document, partially explain, and not reliably reproduce through the means those craftspeople used. The gap is not theoretical, it is practical. It is the gap between understanding something and being able to do it, and it is, in every case, a direct consequence of the loss of the tacit knowledge that linked the understanding to the action. In 1975, a team working in the Bolivian highlands near the shores of Lake Titicaca excavated the remains of a pre-Columbian smelting facility and found something that changed the direction of an entire research program. The facility showed evidence of tumbaga production, tumbaga being the gold-copper alloy that was the primary working material of Andean metallurgical traditions. But the surface treatment of the tumbaga objects found at the site showed a specific type of enrichment that earlier analysis had not fully explained. The technique, called depletion gilding, involved treating the alloy's surface through a controlled chemical process to preferentially remove the copper from the outermost layer, leaving a surface that was substantially pure gold in composition, while the underlying material remained the cheaper tumbaga alloy. The visual result was indistinguishable from solid gold. The material result was a gold surface, with the mechanical properties and physical behavior of an alloy. Heather Lechtman, a materials scientist and archaeologist at MIT, spent the following decades working to understand this process, not just through laboratory analysis of surviving objects, but through physical reconstruction of the processes that produced them. Her approach was experimental archaeology at its most rigorous. She used period-accurate materials, period-plausible equipment, and empirically derived estimates of the process variables, running physical experiments to test whether her reconstruction could produce results matching the analyzed originals. After years of this work, she was able to reconstruct the depletion gilding process with sufficient precision to produce results matching the ancient objects, but only because the physical experimentation revealed aspects of the process that the materials analysis of the objects alone had not disclosed. The tacit dimension of the technique, the specific temperature range, the specific reagents, the specific duration and sequence of the surface treatment was not visible in the product. It was only recoverable through doing. This is the insight that experimental archaeometallurgy the field dedicated to physically reconstructing ancient technical processes, rather than just analyzing their products, has been generating with increasing clarity over the past several decades. The knowledge is not entirely gone. Some of it survives in objects that can be reverse engineered through physical experimentation. Some of it survives in oral traditions maintained by communities who kept the connection to their ancestors' practice alive through the same social fabric that kept it alive originally. The higher communities in Tanzania, where Peter Schmidt's excavations provoked a cultural revival of interest in traditional smelting, have maintained oral memory of furnace construction and operation that still contains technical information not visible in the archaeological record. The indigenous highland communities of Bolivia and Peru preserve fragments of ritual knowledge encoding specific aspects of the bronze casting process. Smithing lineages in Sri Lanka claim maintenance of a steel production tradition related to the Wootz adjacent high-carbon steels of the South Asian tradition, using processes that materials scientists have not yet fully characterized. These fragments are the living ends of broken chains. They are not the complete knowledge, not the full tacit expertise of a tradition that has been maintained uninterrupted. They are survivals, pieces of a larger structure, preserved by communities that understood, at some level, that what they carried was worth carrying. The iron lattice is broken in many places, but a broken lattice still has a shape, and a shape still carries information about what was whole. Imagine spreading 10 maps on a table. Each map shows a different part of the world: Central Africa, the Indian subcontinent, East Asia, Island Southeast Asia, the Andean Plateau, the Mediterranean Basin, the Celtic Highlands of Europe, the Great Lakes region of North America. Each map covers a different period of time, ranging from 8,000 years before the Common Era to the 18th century. And on each map, at various points marked by excavation sites, by artifact analyses, by oral traditions and linguistic evidence, there are markers indicating metallurgical achievements that the conventional story of human technological progress says should not exist where they appear, when they appear, in the form they appear. Looked at one map at a time, each marker seems like a local anomaly, an outlier, a curiosity. The Delhi pillar on its own is an interesting object that doesn't fit cleanly into the standard picture. The higher furnaces on their own are a fascinating regional case study. The Tiwanaku bronze specifications, taken in isolation, are impressive, but perhaps explicable as the product of a particularly systematic local tradition. But all 10 maps together, at the same time the markers align. The dates cluster in ways that are not random. The technical achievements share structural features: preheated air blasts, high carbon steel chemistry, controlled alloy specifications, the encoding of technical knowledge in ritual form that appear across cultures with no documented contact, at periods that the standard framework assigns to technological prehistory for these regions. The pattern is consistent, directional, and global. It does not look like coincidence. It looks like evidence of a single underlying reality seen from 10 different angles. What that reality is, expressed in its simplest terms, is this: the timeline is wrong, not in minor respects, not in peripheral details that can be adjusted without disturbing the larger structure. The timeline is wrong in the fundamental sense that it was built from a subset of human evidence, primarily European and Near Eastern, and applied as a universal description to a world it was never designed to describe. The civilizations that it underrepresents: African, South Asian, East Asian, Southeast Asian, American, were not behind the timeline. They were absent from the methodology that produced it. And when the missing evidence is restored to the picture changes. These civilizations were not early, they were present. What we call their being centuries ahead of their time was not a leap into the future. It was ordinary human knowledge accumulated through observation, refined through practice, transmitted through the only channels available, doing what human knowledge does when it is given sufficient time and sufficient stability, producing results. The results were extraordinary by the standards of the conventional story. By the standards of actual human capability, extended across actual human timescales, they were what you would expect. When the corrected timeline is laid out, plainly stripped of the interpretive filters that the conventional framework applies, What it shows is not a series of anomalies clustering around an otherwise sound narrative. It shows a different narrative entirely. In Africa, sophisticated furnace metallurgy was operating by at least 2500 BCE, with steel production confirmed by 1400 BCE, in a region that the standard account places in the Stone Age for the duration of both periods. In India, iron smelting sophisticated enough to produce consistent high-carbon steel was in practice by at least 1000 BCE, with the Crucible process for hypercarbon steel, the process that produced carbon nanotubes as a byproduct of its chemistry, established by 300 BCE. In China, cast iron production was underway by 700 BCE, followed rapidly by the decarburization process that allowed controlled adjustment of iron's carbon content across a full range, from cast iron through steel to wrought iron. In the Andes, platinum sintering and standardized bronze alloy production were both operating by 300 BCE, in a civilization that had developed its own independent metallurgical tradition without any traceable external input. The pattern of these dates is not the pattern of sequential diffusion from a single source. If metallurgical knowledge had spread outward from one origin point in the Near East, as the conventional story broadly implies, the dates would show a geographic gradient earliest in the Near East. Later, as you move further from that center, they do not. They show a distributed, roughly contemporaneous emergence of sophisticated metallurgical capability across multiple continents, with the African evidence potentially the earliest of all. This is the shape that a genuinely global human engagement with metal actually makes, when all the evidence is allowed into the picture. It is not the shape of a single civilization teaching the others. It is the shape of a species discovering the same territory from multiple directions simultaneously, some through independent paths, some through the maritime and overland networks that connected the ancient world more thoroughly than the standard history acknowledges. The Iron Age, understood correctly, was not an age at all. It was a condition, a state of knowledge available to human beings in multiple traditions, across multiple periods, arrived at through multiple routes, and sustained through the social mechanisms that every culture developed to keep what it had learned alive for the generations that would follow. The pillars and blades and furnace ruins that remain are not the relics of a primitive past. They are the physical record of a sophisticated present, a present that existed long before the one the textbooks described, in places the textbooks barely looked. The evidence gathered across the civilizations, examined in this documentary, points toward three conclusions about the nature of human intelligence and the sociology of knowledge that have implications extending well beyond the specific force. History of metallurgy. The first is that technical sophistication does not require formal scientific institutions. Every ancient metallurgical tradition examined here, the Haya, the Vincha, the Shona, the Indian crucible smiths, the Chinese blast furnace operators, the Andean cosmological metallurgists, achieved results that match or exceed modern capabilities in specific domains, without universities, without written theory, without the institutional infrastructure that the modern world associates with serious science. What they required was time, systematic observation, effective transmission, and the freedom to practice. These are not lesser prerequisites than the ones modern science requires. In some respects, they are more demanding. They require a social stability and a cultural commitment to the continuity of knowledge that industrial civilization has proven repeatedly unable to guarantee. The second conclusion is that the destruction of cultural frameworks is also the destruction of the knowledge those frameworks contain. The Wootz tradition in India was not stored in books that could be preserved when the cultural context was disrupted. It was stored in people and in the relationships between people, in the specific social forms, the hereditary craft family, the master-apprentice bond, the ceremonial context of practice that maintained the conditions for its transmission. When British colonial administration disrupted those social forms, the knowledge that lived within them died. This is not metaphor. The steel that Wootz could produce has not been made again in the same way by the same methods. The loss is real, physical, irreversible in its current form. And this pattern, cultural disruption as technical knowledge destruction, repeats across every civilization touched by colonial encounter. The full technical cost of colonialism has not been calculated. It cannot be. because we do not know the full extent of what was lost. The third conclusion is the one that should give the greatest pause. The emergence of modern scientific institutions and the disappearance of ancient technical traditions are not simply sequential events in a story of progress. They are causally linked, and the causation does not run only in the direction of improvement. Modern science in its institutional form arrived with a self-understanding as the replacement for pre-scientific knowledge, superior, more reliable, more productive of truth. What it actually replaced was not inferior knowledge, it was different knowledge. Knowledge organized around different priorities, stored in different media, capable of different things. The ancient Indian Crucible smith possessed practical knowledge of steel chemistry that modern theoretical chemistry has not yet been able to fully translate into the ability to reproduce the original result. Modern chemistry can explain what Wootz is. The ancient smith could make it. The explanation and the capability are not the same thing. And we have been treating them as equivalent for long enough to have allowed the capability to disappear. There is a broader implication in this third conclusion that the evidence pushes toward, even if it cannot be stated with certainty. Every knowledge system reflects the priorities and constraints of the civilization that developed it. Modern science is extraordinarily powerful at generating theoretical understanding, at identifying mechanisms, at building predictive models of complex systems. It is organized around the production of transmissible, verifiable, scalable knowledge. Knowledge that can be written down, reviewed, reproduced in any equipped laboratory anywhere in the world. These are profound capabilities. They are also specific capabilities, shaped by specific institutional histories and specific cultural priorities. The knowledge systems of the ancient metallurgical traditions were organized around different priorities, around reliability of outcome under field conditions, around transmission through social bonds rather than written documentation, around the integration of technical practice with the cultural and spiritual frameworks that gave that practice meaning and motivated its continuation across generations. These systems were also extraordinarily capable within their own domains. They produced carbon nanotubes, platinum sintering, preheated blast furnaces, standardized bronze alloy ratios, maintained across continental distances, all without the theoretical vocabulary that modern science uses to describe what they accomplished. The honest recognition of what this means is not comfortable. It suggests that the progress narrative, the story of a single ascending line from primitive ignorance to sophisticated knowledge, is not a description of how human understanding actually develops. It is a story that a particular cultural tradition tells about itself, applying its own evaluative criteria retroactively to traditions organized around entirely different criteria. And the cost of that story, paid in lost knowledge and misunderstood history, is still being tallied. In 2019, a research team at the Indian Institute of Technology, Kanpur, began a project that connected two kinds of knowledge that had been separated for approximately 150 years. On one side of the collaboration were materials scientists, with access to modern spectroscopic analysis, electron microscopy, and the full resources of contemporary metallurgical research. On the other side were informants from surviving South Indian smith communities who had maintained, in fragmentary form, oral and practical traditions related to the crucible steel process that their ancestors had practiced. The oral knowledge was not complete. It was not sufficient, on its own, to reproduce the process. But it contained information that the materials analysis had not disclosed specific details about the crucible composition, the timing of specific stages, the sensory indicators used to manage the process that directed the experimental work toward parameter spaces that the purely analytical approach had not explored. After several years of combined experimental and traditional work, the team produced a batch of steel using a traditional-style crucible smelting process that showed, for the first time in approximately 150 years, an authentic Wootz microstructure, including carbide banding. Including, on electron microscopy examination, the nanotube structures that the Dresden team had found in the 17th century blade. The knowledge chain had not been destroyed. It had been distributed, scattered across the objects in museums, across the analytical papers in journals, across the memory of communities that kept the practice alive in incomplete form, across the physical intuitions of smiths who had never stopped working, even when the tradition around them had collapsed. The pieces had been in different places, in different forms, waiting for a project that was willing to treat all of them as equally real sources of knowledge, rather than ranking the modern scientific knowledge above the traditional and discarding everything that didn't fit into the accepted categories. This is not the end of the story. One batch of authentic Wootz steel, produced in a research laboratory after a multi-year collaboration, is not the restoration of a tradition. The complete tacit knowledge of the process has not been recovered. The specific sensory understanding that would allow a single skilled practitioner to produce the result reliably, alone, using only traditional materials and equipment, without modern analytical support, that understanding is still gone. The work of recovery is not complete. It is, in many respects, barely begun. But it is happening. In Tanzania, the higher community's engagement with the history of their own smelting tradition, initiated by Schmidt's excavations in the 1970s, has grown into an active cultural project in which younger community members are learning the oral knowledge held by elders and archaeologists, are documenting the technical information encoded in that knowledge. In the Bolivian highlands, collaborative projects between indigenous communities and academic researchers are slowly recovering the procedural details of bronze casting techniques that survived only in ceremonial form. In laboratories in London, Ankara, Chennai, and a dozen other places, experimental archaeometallurgists are building reconstructed furnaces and operating them with period-accurate materials, learning things about ancient processes that could not be learned any other way. These recovery efforts share a common orientation that distinguishes them from earlier approaches. They treat traditional knowledge and scientific analysis as equal partners, rather than as a primary and a secondary source. The traditional knowledge is not merely picturesque context to be noted before the real analytical work begins. It is data of a different type than spectroscopic readings or isotopic ratios, but data nonetheless, carrying information about the practical process that physical analysis of the products alone cannot recover. The combination of these two types of knowledge, the analytical and the traditional, the theoretical and the procedural, is what the Kanpur Wootz project demonstrated, and what the broader field of experimental archaeometallurgy is now actively building on. What this means, practically, is that the recovery of ancient metallurgical knowledge is not simply a historical or archaeological project. It is a scientific one that has the potential to expand what modern materials science understands about the relationship between process and outcome in steel and alloy production. The ancient traditions achieved results through empirical routes that modern theory has not fully mapped. Following those routes backward, understanding why the specific process worked, what variables it was controlling through sensory judgment rather than instrumentation, what the tacit knowledge was actually encoding in terms of physical and chemical parameters, is a path toward understanding that moves in both directions simultaneously. It recovers the ancient, it enriches the modern. The iron lattice was never destroyed. A lattice whose threads are severed in many places is still a lattice. Its geometry is still legible, in the right light, to someone willing to look at the whole shape rather than fixating on the breaks. The work of recovery of tracing the surviving threads back to where they came from, of understanding what was known and how it was known and by whom, and of connecting that understanding to the technical capabilities that modern science brings. This is the work that the evidence demands. It is not archaeology in the conventional sense. It is not material science in the conventional sense. It is something for which we do not yet have a fully adequate name. A practice of recovering human knowledge from the places it survived, rather than lamenting the places it was lost. History, as it is usually told, is a line moving in a single direction, from less knowing toward more knowing, from primitive toward sophisticated, from the dark past toward the illuminated present. But the evidence described in this documentary points toward a different shape entirely. Human knowledge is not a line. It is a lattice, a structure of connections across time and space, some intact, many severed, all of them carrying more than we assumed when we first looked at them from the angle of a framework that was built to see only one part of the world. What the lattice reveals, when viewed complete, is not a story of primitive peoples stumbling accidentally toward the achievements that properly belong to modern civilization. It is the opposite, a story of modern civilization slowly, incompletely, and with considerable difficulty beginning to recognize what human beings were capable of doing long before the institutional frameworks we built to manage knowledge came into existence. The carbon nanotube in the ancient blade was not there because the ancient smith was ahead of his time. It was there because his knowledge, organized differently from ours, moved through different channels to different results. Results that our knowledge, organized as it is still working to fully comprehend and reproduce. The iron at the center of this story was never simply a metal. It was a question that ancient hands asked of the earth and answered with fire and clay and patient observation over generations too numerous to count. That question was answered in different languages, in different climates, in different furnaces, by people who did not know each other and who are remembered, if they are remembered at all, in the narrow margins of a history that was written by others about other things. But the answers they found are still in the world. In a pillar standing in Delhi, refusing to rust. In the atomic structure of a medieval blade, visible only through instruments the blade's maker could never have imagined. In the memory of elders, in the dimensions of sacred objects, in the chemical signatures of ore and metal that have been waiting in the ground for someone to read them correctly. The lattice is still there. It was always there. The work now is not discovery. It is reconnection, the slow, patient, necessary work of understanding what was known, how it was known, and what it means that we forgot for so long to ask. Every furnace ruin waiting beneath the African soil, every blade analyzed under an electron microscope in a European laboratory, every elder whose memory holds one more detail about a fire their grandfather taught them to read, all of it is part of the same structure, waiting for the right scale of attention to make its shape visible. History is not finished. Neither is the iron lattice. Both are still being written, in labs and excavation sites and community conversations, by people who have understood that the past is not behind us. It is distributed around us, present in the objects and the memories and the earth itself, asking to be reconnected into the whole it always was.